I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
Physics,
medicine,
nature,
or
Space. Time.
the brain, life.
The universe.
This week, does an abundance of facial hair mean a man is really fertile? What does a black hole actually look like? And why does eating something really cold sometimes cause a splitting headache? These are some of the questions that you've been sending in and that we're going to be answering. Hello, I'm Chris Smith, and this is The Naked Scientists.
The Naked Scientists podcast is powered by ukfast.co.uk.
Well, let's meet the team who are going to be answering your questions for you this week. David Rothery is a Professor of Planetary Geosciences. He's with the Open University. Hello, David.
Hello, Chris.
So what have you got that's exciting news from your neck of the scientific woods this week?
Well, not so much exciting as depressing. There's another paper out suggesting that we redefine what the word planet means, and I wish people just leave it alone and give up on Pluto. It's not a planet. It's absolutely amazing and fascinating, but it's something else. We've got 8 planets, and then we've got all these other bodies which geologists work on as if they are planets, but you've got to draw the line somewhere.
Was it a sort of fit of pique and pedantism that led to the diminution of Pluto down to dwarf planet status? Or was that actually based on sensible scientific rationale and we should have done that all along?
There was a realisation that the term planet had never been defined. So the International Astronomical Union about 12 years ago now said, right, we need to define what planet is. Because so many bodies had been discovered out where Pluto is that are similar to Pluto. Pluto's not outstanding in any way. There's so many other Pluto-like bodies there. The obvious division between what's a planet and what isn't is at Pluto-like bodies which cross Neptune's orbit. They're a different class of body. But as a geologist, as a planetary scientist, you can work on Pluto because the same processes go on. But it would have been a mess to have Pluto and all the others as planets as well.
I'm really pleased that in this day and age that space scientists, with all these amazing mysteries of the universe to solve, are grappling over something as complicated as actually how we define a planet.
Nobody's defined moon. And people have a go at me about not having a definition of what's a moon and what isn't.
I thought that was something that people did with their trousers down.
Well, there's that as well.
We'll leave it there. David Rothery from the Open University. He'll take your space science questions. Now, Anna Porjajski is also here. She's a materials scientist and also a stand-up science comedian from University College London. Hello, Anna.
Good evening.
So what can you tell us about being a science comedian? Because many people think science is dull and boring. That's why we're here to disabuse them of the notion. But how do you approach that?
Absolutely. So I do science comedy to comedy audiences who often they're not expecting comedy to come from a scientist. So we sort of trick them into hearing about science under the guise of comedy.
So what do you do? Walk out with a test tube and then say, have you heard the one about...
Yeah, occasionally I'll do some demos or I'll just be talking about general scientific concepts and trying to find some interesting things that people will enjoy hearing about in my field of materials.
So this chemist got sick and the family took him to the doctor and the doctor said, they said to the doctor, look, if you can't helium or curium, you're going to have to bury him.
Very
you can
good.
add that to your repertoire.
I'll
Thank you
add
very
that
much.
one in.
So that's Anna Porjajski, and she is from University College London, and she's a materials scientist. So actually she'll be answering your questions about things to do with what the world is made of and what things around us are made of. Now, Amy Eckhart is also here. She's a PhD student from the University of Sussex, and you're going to do biology for us this week.
Right.
Amy, you're a PhD student studying what?
Yes, so that's right. I'm a PhD student at the University of Sussex in Brighton, and I research how breast cancer cells undergo cell division.
What's cell division?
So that is when a cell grows, doubles its DNA, and splits perfectly in half from 1 into 2. And this is how we all came into existence from a fertilised egg. It's how we grow, and it's how we repair injuries. So it's super important, but it's also how tumours grow.
And so understanding the basis of how tumours grow is important if we want to find a way to treat them.
Exactly.
Thank you very much. So any questions on biology, cells, perhaps even cancer, they should go Amy's way. So she'll be there to answer those. And also Michael Conterio is here. Michael's a physicist. You're also a former radio DJ. Not many of those around, are there? Physicists who have turned radio DJs. Michael, you are now working for an organisation that's called Isaac Physics. What's that?
So it's a project aimed at mostly A-level students and basically trying to set them problems in such a way that they think more like physicists have to as they go on to university and later on. And so we've got lots more challenging problems which have stuff that you might learn at school, but you have to think about it in a different way. And we do this online and in live events across the country.
What do you mean by think about it in a different way?
So it can be something that's quite simple. One of our favourite problems that we've got is just about two different vehicles braking at different times and stopping at the same time, and what has to be different between those. Because so many people just, when they think about these things, go straight to the equations and don't actually think about what's going on. And we basically want to start with simple problems like that, and then we can just make them more and more complicated. But if you don't think carefully about what's going on and just try and write down a simple equation, you'll never get to the answer.
I suppose you're saying you want people to think about why we apply an equation rather than just learn to solve a problem by rote, by learning, oh, it's that kind of problem, I need this equation, and actually don't understand any of it.
Yeah, that's precisely it, because there's so many different parts of physics and there's not these fixed boundaries between them. It just all kind of merges into one.
So Michael is here to make your physics simple. Now, if you'd like to get in touch with all of us and put your questions in, you can phone up 03459 25 2000 on the telephone. You can email chris@thenakedscientist.com, or you can tweet @nakedscientist. Now, first up, listener Sasha has been in touch, and what Sasha would like to know is why we're searching specifically for Earth-sized planets. David, is there something special about the size of the Earth, for instance, that makes life more likely?
Well, there is something special about the size of the Earth, Sasha, but we're not searching specifically for Earth-sized planets. We're searching for any planets around other stars that we can find. And most of them are giant planets like Jupiter, because they're the easiest ones to find. If one of those goes in front of a star, it cuts out more of the star's light, for example. But we are now beginning to find Earth-sized planets transiting, going in front of their stars and causing a tiny dip in the brightness. And that is what gets people most excited, and that's what hits the news. Just about 10 days ago, there was a story broke with 7 Earth-like or Earth-sized planets orbiting a star known as TRAPPIST-1. We'd known about 3 of them for a couple of years, actually, and 4 more were announced, taking the total up to 7. That was very exciting. It was a red dwarf star, 7 Earth-sized planets. At least 3 of them are going to have the right temperature for there to be liquid water on the surface. So it's a place where life that we understand could form, and where life that we understand will be detectable by means that we have. Now, nobody's saying you're not going to get life in the clouds of a Jupiter-like planet, but that is highly speculative. So if we want to find life elsewhere, the most sensible place to focus on, to begin with at least, is planets that look similar to the Earth. Then at least we have a chance of looking for something that we can recognise.
One point that was made to me this week in the wake of this discovery was that because those small planets are so close into that host star, which is, as you say, not much bigger than Jupiter, they will therefore become what we call tidally locked. So they'll always show the same face to that star in the same way that we always see the same face of the moon. And that will mean that one side of those planets is going to be roasting hot or nice and warm, the other side very, very cold. So it's not going to be ideal and not like the Earth at all, potentially.
Unlike the Earth in that respect, this tidal locking is because it's a small, dim red star, and to be at the right distance from it to be warm enough, you've got to be very close and you get tidally locked. But that doesn't mean one side is roasting hot and the other side is absolutely freezing. If it has an atmosphere and some circulation, the heat will be distributed around the planet. So you could have life all over the place. No sunlight, no starlight on the far side, but there are ways to feed off chemical energy. So they are in the habitable zone. The temperature, we believe, is conducive to liquid water. And if you've got the right chemistry, you can have life. So being tidally locked, most of the life-bearing planets in our galaxy could be these Earth-like planets round red dwarf stars, tidally locked. We could be the unusual case, not the norm. We don't know yet. It's exciting that we're beginning to find out.
It really is very exciting. Thank you, David. Amy, before we go into any more of the questions, there's been a recent study conducted at Imperial College which surprised a number of people because they were told that 5 portions of fruit and veg a day, which we thought was conducive with good health, is now not enough, and we've got to double it. Now, how did this come about?
Yeah, so there's been a heck of a lot of confusion over how exactly much fruit and veg we should all eat, and if any particular types are especially beneficial, because a lot of companies like to use the health benefits of vegetables for marketing, like, so-called superfoods and what have you. What this group of researchers did, they did something really cool. It's called a meta-analysis. So That's basically pooling a lot of similar studies together in order to really detect benefits or harms of different things. So in this particular instance, looking for if there's any real benefits of eating more fruit and veg. And they found that eating more fruit and veg was beneficial up to a point. And they found that overall eating up to 800 grams of vegetables a day, so that's the equivalent of maybe 10 portions, or another way to visualise 800 grams is that's about the size of a loaf of bread, that much vegetable a day. That provided the maximum possible benefit against heart disease, cancer and general mortality. But any more than that made no real difference to mortality. So eating more fruit and vegetables is good, but that benefit doesn't increase exponentially. So if you eat kilos of vegetables, you're not going to live forever.
Is it that if you say eat 5, people will eat 2? If you say eat 10, you have half chance that maybe people will eat enough?
So I think one of the intimidating things for me is I get confused about what a portion is. A portion is maybe less vegetables than you might imagine. I often envision piles of broccoli when I hear headlines like, oh, you must eat 10 portions of fruit and veg, but 80 grams, it might not be too much. It could be, I'm a massive fan of putting vegetables in my curry, or I'm a big fan of frozen peas or the frozen vegetable section, for example.
I'm a big fan of Shiraz. Can I include wine in my 5 a day, 10 a day? Good, I've got the official nod from Amy. Thank you very much. Michael, back down to earth now, and with a bump, because we've got a question for you from Addy, who says, if I were trapped in a falling elevator, could I jump at the last minute right before it hits the ground? And if I could jump, would that mitigate the effects of the fall on my body?
Oh, this is quite a shame, because when I was young, I had this exact same question and thought, it would be brilliant just to be able to jump at the end and save my life. But as it turns out, you can't, sadly, because if you think about it, if you imagine falling all the way down from a few floors up, then of course you're building up speed, you're building up momentum as you go down. And when you reach the bottom, it's the fact that in order for all that momentum to be, for you to lose all that momentum, the floor has to basically push on you very hard, and it pushes on you so hard that it hurts, it breaks your legs and kills you. And so if you could do a little jump just before you reach the ground, you're not going to be able to get rid of all that momentum. You can only jump a little height compared to how much you've fallen. So you wouldn't have the strength to do it. If you did have the strength to do it, you'd still basically break your legs while doing it. And there's also the fact that if it's in free fall, so the lift is just dropping, there's no friction keeping it up or anything, then you would be in free fall as well. And that means that the slightest touch on the bottom of the lift, you'd start drifting away from it. Your acceleration would be slightly different to the lift. So there's a big result in general relativity, which basically says being in free fall inside a lift like this is basically the same as being out in deep space and just floating around in a rocket ship there. So you'd experience almost like zero gravity while you were falling for those few brief moments.
I suppose one way you could also look at this is to say that in order to have movement which is equal and opposite to the falling of the lift, you've got to jump as fast in the opposite direction as the lift is carrying you downwards. So you've got to be going upwards at the same speed as the lift would be going downwards and you splatting on the ground. So in order to propel yourself at that rate anyway, you'd have to actually experience the same forces on your legs to accelerate you, wouldn't you, in the first place? So you'd still do damage to yourself achieving a monumental jump like that.
Yeah, it's basically the same as saying that you're going to be accelerated to that level, that speed, whatever speed you've achieved by falling with the lift, in the same amount of time as it would take you to jump, which is a lot of force in a very little time.
Michael, thanks very much. You're listening to The Naked Scientists with me, Chris Smith. Still to come, we're asking what happens to your body when you run a marathon. Why do we get brain freeze when we eat something really cold? And we also discuss how exoplanets are named, complete with some of the suggestions that you sent us from Twitter and Facebook. Anna, here's a quick question for you.
Is spider silk the strongest natural material?
So you're our materials scientist. Spider silk, what's special about it, and is it the strongest material?
Well, spider silk is is an example of an exceptional natural material. It's exceptionally strong and it's also very, very stretchy. These are two materials properties that we don't often see come together in a single material. However, it is not, unfortunately, the strongest natural material. In February 2015, it was surpassed by limpet teeth. These can be up to 40% stronger, actually, than spider silk. And the reason that they're so strong is that they're an example of a nanocomposite. What we mean by that is a composite is a combination of two different materials, one of which is at the nanoscale, so very, 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 very thin. Now, this particular material of limpet teeth is made from a protein base, and interwoven in that is a dense webbing of very, very tiny nanofibers made from an iron-based mineral called goethite. The combination of properties of these proteins and this mineral that give the limpet teeth their incredible strength.
And they need that incredible strength because...
Well, because they've got to hang on to rocks no matter what the weather is or no matter what kind of predator.
Is it that, or are they because they're scouring stuff off the rocks?
Oh, I'm not actually sure.
Because they're grazing, aren't they? As they go across the rock surface, they're sort of scraping off algae and things and filtering them into their body.
So they need...
So I suppose you need something harder than the rock you're living on. Otherwise your teeth are going to wear away really fast.
Indeed, not only harder but stronger as well. And so, yeah, the materials properties required are pretty intense for these poor little limpets.
So spiders are trumped.
Yeah, unfortunately they are.
By a limpet.
Yeah.
Thank you very much, Anna. Amy, this came in for you.
Hi, my name is Hong, calling from Melbourne. I have a question. I was just wondering, how do plants make stem cells? Is it the same way as vertebrates, or is it made in a seeding stage? Thanks.
Amy, you better begin, first of all, by telling us what a stem cell is that Hong referred to there.
Sure. So stem cells are what scientists call, because scientists like big words, undifferentiated cells. And what that means is the cell has the capability to turn into any other type of cell in the body or the organism, such as a plant. So, for example, in us, we've got heart cells, we've got brain cells, stomach cells, skin cells, but they all started life as stem cells. A nice metaphor I like to think about is stem cells are a little bit like children. Their future is stretched out before them and they have the capability to become whatever career, whatever job they want. And depending on the environment that child is placed in and what education it's given, then that determines its future. So stem cells are like children, and then once they become more specialised, once you choose your job, such as a physicist or a radio presenter, it's much more difficult to break out of that and become something else. Plants do have stem cells because, and this is important for plants, because plants are not like us or animals where they can run away or move away from danger. So if they get eaten or damaged by bad weather, they need to be able to regenerate themselves, of course. So yes, in areas of the plants where growth takes place, so the shoots and roots, there are stem cells.
I think they go by the name meristems.
Yeah, that's the region of the plant tissue where the stem cells are found, yes.
Good job we have them, because otherwise...
Yes.
Because Anna was telling us earlier she's gone vegan, and you'd be very hungry if it wasn't for stem cells growing lots of plants for you to eat.
That's absolutely right.
David?
Well, if plants didn't have stem cells, wouldn't they be all floppy? Fall over.
Well, yes.
Very good. Anna's the comedian, David, just to...
Stay in your lane,
challenging.
Yeah? I like that phrase, stay in your lane. Right. Now, it's almost time for our fruit and vegetables quiz, talking about fruit and vegetables. But first of all, got this question for you, Michael, which is coming from Tim.
I've heard that the Event Horizon Telescope is currently trying to capture the first ever image of a black hole. What on earth will it look like?
Michael, what will a black hole look like? And how on Earth, or how in space, are scientists trying to actually image one?
In a way, the clue is in the name, and that the actual black hole itself will look black. There won't be any light coming to us from that. But that's just part of what's going to be happening kind of around the black hole. Because obviously the gravity around the black hole is quite strong. You'll have all this other material which is getting sucked up and getting pulled towards the black hole, and in some cases kind of almost orbiting it. That's how we've recognised that there are black holes already. We haven't seen one directly so much as seen the effects of one on other planets of other solar systems. And so all of this material swirling around it, it crashes into each other, it gets hot, hot things will start to give out light. And so you'll kind of see this kind of swirl of light around the black hole. And of course, it's even more complicated than that, because black holes warp space and time around themselves. And so around near the black hole, some of the things that you'll see when you're looking nearly at it will be stuff that's behind the black hole. The light that has come from all of the material crashing into each other behind it will bend around the black hole. To the light, it seems like it's going in a straight line. We know light goes in straight lines, but the actual space is warped around the black hole, and so we'll see some of the light from behind it. And this is called a gravitational lensing. In some cases, we've imaged other galaxies, I believe, from behind black holes or just large concentrations of mass.
Why is it helpful to be able to see and image and shape these black holes in this way?
Well, we've got lots of predictions about what is going on in the vicinity of a black hole. Einstein's general theory of relativity is what we need to use in order to describe a black hole. And basically it's a case to just say, have we got this right? Can we actually check this against the universe? Because if we see something that we don't expect, then our theories are wrong.
Blimey, that'd be a worry, wouldn't it? But mind you, that some physicists say it's kind of good to be wrong, because it shows that you don't understand everything and it gives you something to aim at. You then know what the next question is you have to ask.
There was a brilliant line I saw in Dara O'Brien, the comedian, give in one of his shows, which was, "Science knows that it's wrong sometimes, because if it wasn't, it would stop." and that would be it. So yeah, it's always exciting, even if you think that the results that you didn't expect might just be experimental error, like the one about neutrinos possibly traveling faster than the speed of light that we had a few years ago. Even when you think that it is a mistake, there's still a chance that it might be some new physics that we haven't worked out yet, and that's really exciting.
Fantastic. Michael, thanks very much for that one. Now, I don't know about the rest of you, but all of this talking is making me a little bit thirsty, and it seems like Bhavesh feels the same.
If the purest water is meltwater from glaciers, would the frozen water from Enceladus, Titan, or the Moon or Mars's frozen polar ice caps be drinkable to us?
So, David, what do you think?
OK, Bhavesh, well, I'm not sure that the purest water is from glaciers, but let's assume it is. Water on the Moon. There is water in permanently shadowed craters near the Moon's poles. There's quite a famous paper about that, subtitled "Don't Drink the Water," because
why?
It's probably got cometary volatiles in there as well, so it'll have all these organic and carbon-bearing molecules as well.
They presumably haven't tasted Cambridge tap water lately.
But I have, and it's probably worse on the Moon.
Okay.
Titan is going to have methane and ethane tainting the ice. Enceladus and Europa are going to be all kinds of salts, possibly magnesium sulfate, well, Epsom salts if it's hydrated. So you drink that water, you'll be trotting off to the loo quite soon.
Well, that's true, because magnesium sulfate is a pro-diarrheal, isn't it? But there are these people in America where fracking is going on, they're being able to set light to their tap water with methane and ethane coming up with the water. So I suppose they're already used to this.
Well, possibly, but you can't set fire to the water on Titan because there's no oxygen from methane to burn with.
And you couldn't open a nightclub on the Moon either because there's no atmosphere. Yeah. but more seriously, so if we do go to Mars, because one of the really important things, the points that people make is we go to Mars and we're going to have plenty of water because Mars was once very wet. There's loads of subsurface water. Could we just dig a hole, pull out some of that ice and drink it?
You would want to purify it. Just evaporate it and recondense it. Distill it, basically. And the purest form of water is distilled water. Get some steam and condense it. The stuff is sold as glacier water, and it's got little bubbles of air that's been trapped there since the Ice Age, and it's exotic, but I'm not sure. It depends what you mean by pure.
Well, there was a newspaper did a study a week or so ago, and so it was a newspaper study. So obviously you've got to take this with a pinch of salt, unlike what they're saying about the water. But they actually bought a whole range of these things, off the shelf. Some of these very high purity glacial and iceberg water, and of course icebergs are off of glaciers, aren't they? And also just standard common or garden tap water. And they asked a blinded panel of people to taste them all. And they couldn't tell the difference between the glacial water, some of which was retailing at hundreds of pounds a bottle, this stuff. And there was no evidence that people could tell the difference between that and tap water.
I'm sure it felt good, though. If you knew you were drinking water that come from Antarctica, it would have given you a buzz.
And there was thousands of, because the USP is that it's thousands, if not millions of years old, this water. I mean, that's got to affect the taste, doesn't it? I suppose the other question is that if you drink water on Mars, do you have to go to a Mars bar to drink it? Michael?
Other chocolate bars are available.
I just wanted to say, with the water being millions of years old, well, most of the other water has been around a bit. It still probably has been water for quite a long time. It's just been not in a glacier, but when you get down to it, it's water. The water that's been like through several people, and you drink it again, is still as much water as water that's been stuck in a glacier for that long.
Well, this seems the perfect time to bring up this question from Vera for you, Amy, because we're talking about ice and very cold things. And she says, why do we get brain freeze when we eat something or drink something very, very cold? This is this horrible, unpleasant symptom when you have this splitting headache for a fraction of a second after eating things. Why does this happen?
Oh, yeah, brain freeze. I know that well. So when you're eating a delicious ice cream or drinking something really cold, you are rapidly changing the temperature of the blood vessels that are close to the surface of your skin in your mouth, because the blood's really near the surface of the skin. It responds to temperature real quickly, which is why we take people's temperatures under the tongue. So when you change the temperature in some areas of the blood is on its way to the brain. And the brain doesn't have pain receptors as such, but the outer covering of the brain does.
The meninges.
That's right. You've been doing your homework, Chris. So when this cold blood reaches the arteries at the entrance to the brain, the arteries don't like it and they start contracting and dilating, and the nerves around the arteries pick this up, and our body interprets that as pain. And it's a bit of a protective mechanism to say, stop, don't do this. You know, we're a human body. We don't like sudden changes in temperature.
Super. So basically, I put something cold in my mouth, I cool down my mouth, which interprets the localised cooling as oh, my head must be too cold.
Yes, exactly.
And that causes a rebound opening up of these arteries supplying my brain, because it thinks my brain is now too cold and needs more hot blood. Mm-hmm. And that dilatation of the arteries is painful, and I get that headache for a bit.
Yeah.
Super. Well, now I feel much better for that. I mean,
yeah.
So there's nothing I can do about it.
Nothing you can do about it except maybe, cool it with the ice cream. But if it makes you feel any better, this phenomenon's also been reported in pets. So cats and dogs also get brain freeze. Have you been on YouTube recently?
Well, do you know, someone actually said, you know, what would be the hardest question or the hardest thing you'd have to explain about the modern world to someone who was from 50 years ago, who saw how we
Yes.
lived. And the person said, well, I think the hardest thing to explain is how we have access to this amazing thing called the internet, which has all of the information that mankind has ever generated on it, and we use it 90% of the time to share pictures of cats and kittens.
Oh, yeah.
But so go on, explain, how do we know that a cat and a dog has brain freeze then? I'm intrigued.
Oh, maybe it's my bias from viewing this entertainingly adorable cat video.
So let me just get this straight. This is a scientific study done by you, looking at YouTube videos of cats and dogs. So you're saying it's shaky evidence, but there might be some evidence that animals experience this phenomenon.
Yes.
You're listening to The Naked Scientists, and this week we're answering the science questions that you have been sending in. With us, we have a panel of guest experts from the Open University. David Rothery, he's a planetary scientist. We also have Anna Porjajski, who is from University College London and a materials scientist, while Amy Eckhart is from the University of Sussex and a cancer biologist, and Michael Conterio is a physicist with Isaac Physics. Now, little quiz for you, teams. So we're going to divide you up because we thought you're answering other people's questions, but now I've got some questions for you. And we want to find out how well you know your onions, or more accurately, how well you know your fruits from your vegetables. The rule's really simple. We're going to have two teams. We're going to have David and Anna on one team, and then we're going to have Michael and Amy on the other team. I am going to put to you a thing, and you have to tell me if it's a fruit or a vegetable or something else. And, people with the most points get the benefit of knowing that they are the brain of Britain today. Okay, so David and Anna, you're going to go first. The first object is an avocado. Is this a fruit or is this a vegetable or is it something else?
A big stone in the middle. So what does...
It's got a big stone, so that might make it a fruit. But
Or something else. It's not a vegetable.
it's definitely not a vegetable. It might be a nut.
Gonna have to push you. What do you think?
Let's say
It's
something
else, yes.
Is
Going
that
for something else?
Do we don't have to say what, do we? We can just...
David, you talked yourself out of the answer. It was a fruit. It was a big stone in the middle. Okay, right. Let's see if you can improve on this. That won't be hard, will it? To improve on a score of 0 so far. So, Amy and Michael, your food is the tomato. What do you think about that? Oh, there are sour grapes over here. That's not part of the question. Grapes are a fruit, but what do you think, you two?
I've heard that a tomato is a berry, so would that make it a fruit? But I'm going to leave it to you, Mike.
Yeah, I think it's a fruit because I heard some kind of saying or proverb or something about this, which is someone saying, knowing that a tomato is a fruit is knowledge, but knowing not to put one in a fruit salad is wisdom.
Yeah.
So I think it's a fruit.
It's a fruit. Did you like what Amy did there, where she said, "I'll leave it with you"? Okay.
Yeah, passing the buck there.
Passing
yeah.
the buck,
Fruits.
absolutely.
Yeah,
Fruit.
let's do it.
And you got yourself a bing. Good. Right, that's +1 for you two. Right, okay. See if you can redeem yourself, please, David and Anna. Your second food is a pea.
That's a pulse.
Yeah,
Which is a variety of vegetable. But can we say it's a pulse? It's a legume.
Which is a vegetable.
Yeah.
I think we're going to say vegetable.
If it's a binary choice...
No, actually, a pea is a fruit. So that's a brilliant score. You're doing 0 at the moment. That's good. Right, Amy and Michael, back to you. Your next one is sweet corn. What do you think of sweet corn?
My gracious.
Oh, that's a weird one because most fruits tend to be sweet, and sweet corn can be sort of sweet.
I'll give you an example of a sweet vegetable right now, rhubarb. So that throws a spanner in the works.
Gonna have to push you. Should we go vegetable?
Let's go for it. Give the others a chance.
No, I'm sorry. Sweet corn's actually classed as grain.
That makes sense.
Yeah, I'm afraid you got that one wrong. So it's 1 to you and 0 to David and Anna, who we're coming back to. Yeah, you can still everything to play for. David and Anna, on your menu, finally, mushrooms. What do you think of mushrooms?
They're fungus.
Fungus.
Yeah.
They're fungi.
Yeah.
They're certainly not a fruit. Depends how you define vegetable. We've
So
never had a definition.
they're not fruit, they're not vegetable. You're going
It's a
for
fungus.
You're going for other.
Yeah, other. Yes.
Very good. You got a point. So it's 1-1. So this is the big one. If the guys throw this, then it's going to be a draw. I don't know what happens if we have a draw. So Amy and Michael, your final food is rhubarb. Is that is this fruit or vegetable or other?
Well, put my foot in my mouth earlier, so
You did a bit.
I will bear responsibility if my research is wrong. So shall I?
Yeah, you go for it.
I'm going to say vegetable.
Hey!
Why is that? Just explain what your reasoning was. Why do you think rhubarb is not a fruit?
It grows underground.
Underground? Have you ever grown rhubarb?
No. I don't know anything about rhubarb.
It's got those
apart from that
giant
it's
leaves and the red
delicious, and you
stemmy things.
Don't eat the leaves.
It's lovely. No, you don't eat the leaves. Lots of oxalic acid in the leaves. They cause kidney stones. Not good for you.
No.
But the stems, you eat the stem cells. Yes, no, it's the big long red stems. But yes, it is. You're eating part of the plant flesh, so that's actually a vegetable. Well done. So I guess that makes it 2-1 to you guys then.
Well
So this week's brains are Amy and Michael. Very well done. Right, well, we better move on with the science then. If you'd like to ask us a question, by the way, you can email chris@thenakedscientist.com or you can tweet @nakedscientist. Anna, this one has come in for you from a very guilty Georgia.
I borrowed my housemate's woolen jumper and managed to shrink it to about half its normal size in the wash. Can I use science to get it back to normal?
Yes, you can. Now, when you shrink a woolen jumper in the wash, what you're doing is a process called felting. And to understand felting, we have to zoom in and look at what a wool fibre looks like at the micro scale. So wool fibres, funnily enough, have tiny scales on them. Now, ordinarily, these scales lie flat against the wool fibre. But what you're doing when you wash your jumper in a hot wash is you're messing up these scales, so they end up pointing upwards rather than along the wool fibre length. and they get snagged on each other, and this is what causes the tangling. Now, anyone that's ever backcombed their hair will be familiar with felting of hair, because this is exactly the same process. So what would you do if you had backcombed hair? Well, you would wash your hair with conditioner to smooth out the fibres again and to get those scales lying down. So this is exactly what you should do with your woolen jumper.
You condition the jumper.
Just normal hair conditioner, and if you massage it into your woolen jumper and gently stretch it out, you should find that will unshrink your woolly jumper.
Have you tried this? I've never heard anyone suggest that it's amazing. Does it really work?
I haven't tried it, but I've seen it happen on YouTube.
Oh, well, it must, in that case, it must rather like these animals with brain freeze. It's got to be true.
It's definitely happening. Yeah.
No, because there was a gentleman I interviewed a couple of years ago who'd actually worked out how to unboil an egg. Oh. And it's sort of similar in the sense that when you put egg into very hot water, you denature the proteins. In other words, you make all of the proteins refold in a way that's not the normal way they would fold up to make something egg-like, and it adopts the cooked egg appearance. If you chemically brutalise that material and heat it up, you can rearrange the folding and get it to refold the right way, so you can chemically unboil an egg. So I wouldn't advise putting conditioner on the egg, but you can, in theory, reverse that process, and it's sort of similar. Michael?
Well, that's a really interesting one, because I know a lot of people talk about the concept of entropy in physics, and they use the idea of an egg being boiled or cooked somehow, and say you can cook an egg, you can't uncook an egg because it would bring back order, and that's not what happens in the universe. But the thing that people always miss in those discussions is that the rule in physics is that the entropy of the universe always increases. So you can make something more ordered, so you can perhaps bring this woolly jumper back to its old state, and by smoothing down all of the scales, but you have to somehow make some disorder somewhere else, perhaps in what remains of the conditioner.
You can, of course, make a woolly jumper with genetic techniques, because what you do is you cross a kangaroo, where in the country I've just flown back from, with a sheep, and you get, of course, a woolly jumper. Now, David, we've had a lot of fun with this next question, which is from Adam, and he wants to know how we name new exoplanets. There were 7 ones that were discovered recently. You talked about them earlier. They're called TRAPPIST-1A to F at the moment. We thought that was a little bit boring, so we asked for some suggested names on Twitter and Facebook. Some of the favourite ones that came in, predictably, Planety McPlanetface was from Stephen on Facebook. Also, Colours of the Rainbow, Odysseus on Facebook. 7 Dwarves from Marius on Facebook. And Jeremy wants to name them after different types of alcohol. But actually, how do scientists do this? How do you come up with names for these exoplanets?
Okay, well, the scientific designations for exoplanets are that they follow the name of the star or the catalogue number of the star. And the first exoplanet that you find of a star, actually, you never use the letter A. You
Couldn't
start
you have,
with
David
B.
Bowie? That would be a good star, wouldn't it?
You could have
Tina Turner?
Yes. And then, yeah.
Rod Stewart?
Only for terrestrial planets, because they need to be rock stars.
Yeah, so they have the inner worlds.
Yeah. No. You put the TRAPPIST planets, the TRAPPIST-B, TRAPPIST-1, that's a star, TRAPPIST-1. It was discovered, this star wasn't even catalogued and didn't even have a designation until it was studied. It was studied with a telescope called the Transiting Planets Infrared Survey Telescope or something like that. So from that you construct the acronym TRAPPIST, and then the first star that they studied, TRAPPIST-1, that was the first star that they found to have planets going round it, and then they found 7 planets in total, which are TRAPPIST-1, B, C, D, and E, all the way to H, or however many 7 letters goes. Those are the scientific names, scientific designations. A few years ago, 2014, I think, the International Astronomical Union, the same body responsible for trying to define what planet is in this solar system, said, OK, let's see about giving names to some of these planets. Now, if any of you are offered a chance to buy the name of a planet for a loved one as a birthday present, don't. It's a con. Nobody else will recognise this. The IAU said, let's try out some names. And they put out a call for names, and I'm sure there'll be a call for the TRAPPIST planet names, because it is very close by a star. And it wasn't open to the public. It was open to astronomical societies and the like. And the Astronomical Society of Lucerne in Switzerland, for 51 Pegasi, the first star to have a first sunlight star to have a known Earth-like planet. They suggested the name Helvetios, which is to do with Switzerland, and they suggested the name Dimidium for its planet. And 51 Pegasi b is now Helvetios, and 51 Pegasi b, the planet, is known as Dimidium. Now, I couldn't remember that Dimidium goes with Helvetios. I had to look it up. But I do know that 51 Pegasi b is a planet going around 51 Pegasi. So I'm not sure of these names. They're not meant to supplant the scientific designations. They're meant to be used in parallel. I don't know that they will catch on. I think it's a bit gimmicky. But there are now ways to give names to the stars and their planets. And we'll see what comes of it.
Anna?
Well, it worked with the chemical elements, didn't it? We don't just call them 1, 2, 3, 4, 5, 6, 7, so on.
Yeah, but there are only 92 naturally occurring elements. We've got
We're up to 119 now, aren't
3,000
we?
stars with known planets and 4,000 known exoplanets, something like that. And the number's just going to keep on growing and growing and growing. So,
Michael?
I just like the fact that one of your listeners suggested that they should be named after types of alcohol, because Trappist beer is a thing, and I believe that's where the acronym was kind of like meant to homage the Trappist order of monks, known for brewing their own beers.
Well, I dare say they had that in mind. I've seen some really contorted acronyms. This one isn't bad. Transiting Planets Infrared Survey Test. You can get Trappist out of that fairly simply. But maybe we start with really powerful, hot, short drinks close to the star and have like nice, cool drinks further away from the star.
There's one made with liquid nitrogen, perhaps, like in the nightclub, those test tube
that's
for the distal ones, the distant, far away from the star. Yeah, I like that idea. Thank you, David. Pekka Oilinki on Twitter, @NakedScientists, in relation to your brain freeze point, Amy, says, is there a difference between people from different climates of the world who get brain freeze? So if you live in a place where it's very, very cold, are you less vulnerable than people who live in a hot place, do you think?
I read something about this, and people who know more about this than I do believe that it's less to do with the weather and it's more to do with really the localized sort of temperature change inside your mouth. So, but whether people who live in darkest Siberia or Australia are more resistant or less able to cope with brain freeze, I've got no idea. But I know that if I was eating ice cream on a hot day or eating ice cream on a cold day, I'd still get brain freeze, even if there was a big temperature difference between the ice cream and the weather.
So I can't just change my geography and change my sensitivity to this. David, Chris Heron has been in touch on email and says, we know that Io's volcanism is caused by tidal stresses as the other satellites tug on Io, causing small deviations from a circular orbit. Thus, Jupiter's tidal distortion of Io changes over the orbit, and that generates heat in its interior. But what is losing energy that Io then gains? Is the orbit of Io shrinking, for example, or is Jupiter's rotation slowing a tiny bit?
Yes, it's quite true. You can't get something for nothing. I suspect Io's orbit is actually increasing. It's getting further from Jupiter and therefore orbiting more slowly. And Jupiter's spin will be slowing down very slightly as well. So these tidal interactions are robbing energy from the combined system of Jupiter and its moons.
So as the thing goes around Jupiter, it's getting squeezed and stretched a bit, and that's causing friction in the material of the moon, and that's where the heating comes from in the moon.
You can try this at home. Get a metal coat hanger, bend it to and fro a few times, just touch it to your lips, you'll burn your lips. Well, not badly, but you'll feel the heat. It's this internal friction because of the tidal stressing, and it does the job. But the energy is coming from the Io's orbit and Jupiter's spin.
Anna?
So what you're doing there when you're bending the coat hanger is you're manipulating the atoms inside the metal, and metal in this case is behaving a bit like a plastic, so it's very pliable. And the reason it heats up is because the atoms, as they slide over each other in their atomic planes, are rubbing against each other. And yeah, you're right, that's where the friction comes from. And so it gets released in heat.
Anna, we've got this question. It's probably one for you.
Why do razors go blunt, but diamonds don't?
That question came in from Terry. What do you think?
Thanks, Terry. This is a brilliant question, and it's archetypal materials science, so I'm in my element here.
In your element or in your compound, perhaps? Go
right,
on.
so A razor blade is usually made of a metal, and it's usually made of stainless steel. Now, metals are made of crystals, funnily enough. What we mean by that is that in a crystal, all of the atoms are lined up in a very 3D orderly pattern. Now, in a single razor blade, there are billions of tiny, tiny different crystals. And we call these crystals actually grains, and under a microscope they'll look like sort of crazy paving. So all of the different grains are orientated crystals, orientated different to each other. Now, at the very tip of a razor blade, every time that collides with a hair, it creates a little dent because the atoms at the tip are not very strongly bonded together, and so even the force of a hair colliding with them will cause them to reshuffle. And over time, this causes blunting. Now, the reason I was talking about the grains and the tiny sort of crazy paving crystals earlier was that the points at which they meet are the weakest points in the material. So the fact that there are lots and lots of these grain boundaries means that a razor blade is more likely to have its atoms disrupted by even something as gentle as a hair. Now, in contrast to diamonds are made of carbon, and these carbon atoms are bonded very, very strongly to 4 others. This is a very stable and a very strong structure. Now, diamond is actually the hardest material that we have, and it's down to these carbon bonds. In the case of diamond that wouldn't go blunt, it's probably also because it is a single crystal, so it doesn't have any of those grain boundaries, and so no weak points in its atomic structure.
Basically, if I keep rubbing a diamond up and down a piece of glass, for example, I shouldn't get any loss or damage of the diamond crystal. It'll be the glass that pays the price all the time.
Absolutely. So what we're looking at here is the hardness of the materials, and diamond is the hardest material that we have, so it would always wear away the glass rather than the diamond, yeah.
Well, I didn't know that. Thank you very much, Anna. You're listening to The Naked Scientists with me, Chris Smith. And here's a question on the theme of facial hair. Amy, one for you.
I would like to find out whether or not it is true that if a male has more facial hair, he is likely to be more virile than one that does not have. How does it affect conception?
So David's got the biggest beard in the room. Is he more virile and fecund than somebody who's less hairy, like me and Michael? Yeah.
Oh, well, the short answer is no. So whilst it's true that the hormone testosterone, which everybody produces, men and women, is responsible for beard growth, men all have a very similar amount of testosterone, but it's your individual sensitivity to testosterone that's different, and that is shaped by your unique genetics. A bit how, like, everyone's a different height, everybody's sensitivity to testosterone is a little bit different. So there's an enzyme that turns testosterone into something called dihydrotestosterone, and it's this form of the hormone that affects people's hair. So this eventually causes, well, it can do, if you're very sensitive to testosterone, it can cause the hair follicles on a man's head to shrink in some people. So, sorry, Mike, you're very sensitive to testosterone, but it's amazing how it doesn't affect the follicles on the chin. Like, I can see Mike is perfectly capable of growing a beard.
He's just got his head on upside down. That's what it is.
So, yeah, it's the sensitivity to testosterone, not a man with a full beard is not going to have more or better quality
Sorry
sperm.
to burst your bubble there, David.
Yeah, well, I'd just like to point out that the reason I have a beard is I can't afford a diamond-tipped razor to shave with.
But presumably, Anna, if you did shave with a diamond razor, then you wouldn't end up having to keep replacing your razor every 5 minutes, which is what inevitably happens. You get about 3 shaves and then the blunt. It wouldn't blunt.
Yeah, technically it wouldn't blunt, although I think you'd struggle to get a diamond at a very, very sharp angle like you can with a razor blade.
Oh, so you're stuck then, David. Look, can you squeeze this one in very quickly for us, David?
Hello, Chris and the Naked Scientist team. This is David from the Shetland Islands, and the question is, at what height does zero gravity take effect? And would this vary from different parts of the Earth? And if so, why would this be the case?
So where do we get to zero gravity once we leave the Earth's surface, David?
OK, I think there might be a misconception here that as you get further and further away from the Earth, you're feeling less of a gravitational pull, and at some point you stop feeling the pull of the Earth's gravity. That's not what happens. If you doubled your distance from the centre of the Earth, the gravity would decrease to a quarter of what it is at the surface. But that's not 0G. 0G in space is because you're in a space capsule travelling, accelerating under gravity, orbiting the Earth or going from one body to another, and you're not accelerating, and the person within the spaceship is accelerating at the same rate as the vessel. So it's like the lift dropping down the lift shaft. So 0G is not distance away from the Earth.
So our people who are on the International Space Station, the reason that they are in orbit around the Earth is because gravity is hanging onto them and keeping them in orbit. So, but they're just free falling around the Earth all the time, so they're weightless, but that's not the same as 0G.
Correct. They're in free fall. They're still experiencing the Earth's gravity, but so is the spaceship that they're in. So between them and the spaceship, there's no acceleration.
Because taken to its logical conclusion, the reason that Pluto is 6 billion kilometres from where we are here on Earth and it's still orbiting the Sun is because the Sun's gravity is hanging on to Pluto, even though it's that far away, and gravity does get weaker with distance, but there's still enough to hold on to Pluto and things beyond it.
Absolutely.
Now, Michael, listener Zhao has sent in this question for you.
How many photons do we need to perceive an image or an object? And how much is the upper limit of photons needed to perceive an object?
So what's a photon? Why do we need a photon to see anything anyway?
So a photon is, we call it a particle of light, because in quantum physics, light is just not just a wave, it's also kind of can be divisible into these particular chunks of energy. And we call each one of those for light a photon. You can't kind of have half a photon, but what you can have is photons of different frequency. So for different types of light, they'll have a different frequency and different amount of energy per photon. And the cells in our retina are good at basically detecting particular types of photon, those in visible light. I'm not so sure about what you need in order to get a coherent image, but in experiments, it's kind of really hard to measure exactly how many photons there are, because they're reacting with your eyes and therefore not going to react with set off whatever detector that we're using because they've
so obviously if you were to detect the photon, you couldn't by definition then expose your eye to it.
Yes.
You've got to sort of try and work out some way of saying, well, roughly how many photons must be arriving in the eye to trigger a response in the retina.
Yeah, precisely. But we think that when you're getting down to the order of single-digit numbers of photons, you can just about detect one or a few photons. It's kind of a bit ambiguous there, but you don't recognisably see anything. It's just I think there was something there, maybe. But kind of tens of photons, you pretty much you can. And hundreds of photons, yeah, definitely.
What is the retina doing in order to enable you to detect these packets of energy, the photons arriving on the retina?
So when you get the photon arriving, you're basically transferring the energy from that photon to an electron in the retina, and that creates a signal that can then be interpreted by your brain as having seen some light. But the thing is, it's not all photons that can do this. Some of them don't have enough energy in order to actually bump that up. Because we're getting into chemistry here, you actually get some energies which the electron can't jump up. So this is how you have your red, green and blue cones in your retina, which each respond to a different, effectively sized photon, different amount of energy in a photon. So some of them will just go straight past. Some of them, like ultraviolet light, you won't detect as light. You won't get the right sort of signal, but they can cause the electron to jump up a lot of energy, and that will actually start causing damage in your eye because you've now got a loose electron wandering about, which can start doing damage to the cells in your eye. And on the other end, you have things like microwaves and radio waves, where the photons have lower energy and they just go straight through without interacting with it. There are lots and lots of photons going through your eye that you just never notice. So it's kind of hard to say what's the maximum number. It depends on the type of photon. UV ones will be causing damage. Radio waves will just be going straight through.
I see what you mean, Michael. Thank you very much. I hope you're in the mood for some exercise, Amy, because we've got this one for you from Morgan in California.
What happens to your body during a marathon?
Ooh, that's tough, isn't it? What happens to your body during a marathon? I think apart from the obvious, you get tired.
Yes, apart from getting tired, there's a lot of things. Because you're running for such a long distance, oh my goodness, you're going to use up all of the glucose reserves in your blood, in your muscle cells and also in the carbohydrate stores in your liver. So carbohydrates is your body's preferred source of energy. And once you deplete all of that, your body starts working on fat cells and also muscle cells. So that is going to lead to you feeling incredibly tired, incredibly sore, and the phenomenon called the runner's wall. People describe that as a complete inability to continue and being really unable to focus on anything. Another thing that happens, you lose a lot of fluid, obviously, through sweating. And when you complete a marathon, you actually arrive over the finish line, hopefully, 2 centimetres shorter than when you started because you've lost so much fluid between the discs in the vertebra of your spine. But if you rehydrate properly, you'll be back to normal in 24 hours.
Is this something you spotted on YouTube as well? Or is that a fact that actually people are 2 centimetres shorter after a marathon?
I don't know what you're trying to say about my scientific credentials, but I've done my homework, Chris.
No, it's just your kitten data. I'm just referring. So Mo Farah, right?
Cat,
so Mo Farah is 2 centimetres shorter on average after he completes the London Marathon in record time.
Yes.
Goodness. Okay. And does he inflate again? Presumably he does, because otherwise he'd be minuscule by now, wouldn't he, at the number of marathons he's run?
Yeah. Rehydrate. Yeah. You're back to normal. Yeah.
Wow.
Your original height.
And what other effects are there? Anything else?
Yeah, there's a few more things. Your body needs oxygen to work and do all that exercise. So that's a lot of airflow going through your respiratory tract. And so this really dries out your nose. And so the mucus-producing cells in your nose they work really, really hard. And so your nose will be running a lot, as well as your feet.
Very good, very
good. Your immune system gets suppressed. I think I've heard from runners that they often get a bad cold after doing a marathon. I'm not sure why your immune system gets suppressed in this way. Maybe it's trying to deal with the inflammation in the body from broken and injured muscle cells.
This all sounds like bad news. I mean, is there evidence that marathon runners end up ultimately less healthy than the average person? Because it doesn't sound like a recipe for being healthy.
Yeah, I think it's pretty extreme exercise. Yeah.
So with care.
Yeah.
With care. Thanks, Amy. Now, Anna, Hassan has got a cracking question for you. You'll see where I'm going with this in a second, because Hassan says, what material do they use to make the glass bridges that are appearing all over China? They can be hit with a sledgehammer. They don't break. Surely this isn't normal glass.
Well, it actually is glass, but they've done 2 things to treat this glass so that it is safe for you to stand on a piece of glass hundreds of metres up in the air and be perfectly safe. The 2 things that they do is they toughen it. Now, have you heard of a experiment called a Prince Rupert's drop? This is a very famous experiment done with glass. And what you do is you take a drop of molten glass and you plunge it very, very quickly into cold water. Now, what this does is it has the effect of putting the outer layer of that glass under very, very intense mechanical compression. It's the action of cooling down so quickly that puts the atoms into compression. Now, this means that if you try and put a crack into the surface of that glass, the atoms will just close it up again. It's very, very difficult to get a physical crack into something that is under such intense compression. Now, as we know, physics requires an equal and opposite reaction to a force. So the middle of the Prince Rupert's drop is in very, very intense mechanical stress, tensile stress. So those atoms are being pulled away from each other very, very strongly as well. So yes, you can hit this glass with a sledgehammer and it will be very unlikely to break. The second thing that they do is, this is bulletproof glass, and it is a glass laminate construction. So what this does is this glass is layered and there's layers of plastic in between the layers of glass. So what happens in bulletproof glass is that when a projectile or a person's foot or a sledgehammer tries to hit the glass, then that first layer is probably going to smash. That absorbs a lot of the energy in the bullet or in the sledgehammer. And what it does is then that glass presses down into the plastic layer. And that plastic layer flows sort of like a thick, treacly fudge type thing. And that absorbs a huge amount of the energy and spreads the impact over a very wide surface area. If there's still any more energy in the sledgehammer after that, the next layer of glass might smash and then spread its energy over the next layer of plastic. And so this process continues until the bullet or the sledgehammer is stopped. And that's why you can't fall through the glass.
Wonderful. Thank you very much, Anna. And thank you to our other guests this week. That's David Rothery, Amy Eckhart and Michael Conterio. The producer this week was Tom Crawford. Do join us next time when we're going to be cleaning up space, when we look at the thousands of pieces of junk which are flying around the Earth just waiting to cause us problems. The Naked Scientist comes to you from Cambridge University and is supported by the STFC, the EPSRC and Rolls-Royce. From me and the rest of the team, until next time, goodbye.